Hey, let's take a look at a couple of questions here involving hybrid orbitals and bonding, just to try and kind of put it all together. So for instance, here's a molecule, so let's go ahead and draw it out. So imagine we've got something like H, CH, and we got a double bond, and maybe it goes to, gosh, I don't know, maybe another carbon, and a fluorine, and a fluorine. So imagine we're asked to describe the bonding in this molecule here. And how would we do this? Well, I suppose the first thing we would do is we would apply Vesper. And so we would look at the central atom. In fact, there's not one single central atom here. So I'm going to look at the carbon here that's got three things around it, right? And I'm going to go ahead and say, well, if it's got three things around it, so any kind of bond, any kind of lone pair, right, it's going to have that trigonal planar geometry. And if you've got three repulsions, right, remember that you need sp2 hybrid orbitals. So remember the number of repulsions, okay, so 2, 3, 4, 5, 6 determines the hybrid orbital type. So sp, so sp2, sp3, sp3d or d1, and for 6 you need sp3 D2. So we can see here, if we've got three repulsions, we're going to need sp2 type hybridization here. And again, if we look at the other carbon, so this carbon over here has got one bond, another bond, remember a double bond just we treat as a single bond in Vesper, and a third bond there. So again, it's going to be exactly the same thing. So this guy here is going to have sp2 hybridization. Gotcha. All right, so in terms of the bonding, right, describe the bonding. Well, we can kind of cheat here a little bit. The first bond between a pair of atoms is always sigma. I don't know of any exceptions here. I'm not sure that's 100% true, but for general chemistry, it'll be, I guess, 100% true. So the first bond is always going to be sigma. If there is a second bond or a third bond, so that is going to be a pi bond. That's going to involve some kind of side-on overlap here. So we're going to have 1, 2, 3, 4, 5 sigma bonds and one pi bond in this molecule here. So how are we going to understand the bonding here? So we know that the carbon is going to be sp2 hybridized. So let's have a look at this. So the carbon is going to be sp2. So by itself, it would be 1s2, 2s2, 2p2. And we can draw the hybrid orbital diagram. So we're not hybridizing the 1s. So we're going to take one of the s's and two of the p's. So that's going to give us sp2. And then the p over there we didn't touch. So the third p is all off by itself. And we've got four orbitals here. Now the thing to remember is that all four of these have exactly the same energy. And so we're going to go ahead and put those 4 electrons in. And we're not going to bunch them up in the sp2 hybrid orbitals. We're just going to kind of spread them out. And that's going to give us the ability to make our 4 bonds, right? So whenever we've got an unpaired electron in an orbital, that's going to be 1/2 of a bond. So now if we look at the hydrogens off to the side, we can go ahead and we can look at how hydrogen's going to bond by asking ourselves, what's its electron configuration? 1s1, what's its orbital diagram? It's going to be like this. So all we got to do is overlap the 1s orbital on hydrogen with the sp2 hybrids on carbon. So let's go ahead and go to another slide and have a go. All right, so there's my carbon and my hydrogen and my hydrogen and my other carbon. We've kind of handled the left-hand side. We've got sp2 hybridization, so we know sp2s, they look essentially like trigonal planar, right? So they're 120 degrees to each other, And then my hydrogen, right, I see I've got a 1s orbital with 1 electron in, so there you go. And there you go. And you can see that they're overlapping head on, so that's a sigma bond, and which we said earlier, right, the first bond is always going to be sigma. So that is half of the bonding there. The carbon on the other side, we also said was sp2 hybridized, so it's going to have an sp2 hybrid like that. And remember, they are 120 degrees apart, so there's the other one, there's the other one. And on the other side, right, we have fluorine atoms. So what about those fluorine atoms? Fluorine's electron configuration is 1s2, 2s2, 2p5. So 1s2, 2s2. I kind of like the boxes, don't you? And then 2p5. So 1, 2, 3. So that's Hund. And then 4, 5. So we can see we've got 1 electron all by itself in a p orbital. So the p orbital is going to look something like that. And all we got to do is overlap them. And the best kind of overlap is head on. So we're just going to go ahead and take this fluorine here and this fluorine here. And we're going to do some kind of head on overlap. So let's go with disgusting green. So that's the shape of a 2p orbital. and that's the shape of a 2p orbital, and they are overlapping perfectly, and they're giving us our sigma bond here and here. Oh, and between the two carbons, that was the sigma bond too. So you might say, oh gosh, aren't we done now? We're not actually done yet, because between the two carbons, it was a double bond, and we have forgotten that there are a couple of p orbitals that are currently not in use, and we can go ahead and we can overlap those suckers. So let's draw those, I guess, in white. So we got a p orbital above and below, and another one above and below. Each one has one electron in, so they overlap side on, and they give you that. Do you remember what that was called? Yep, so that is the pi bond. So superimposed on there, you got a pi bond, and it gets kind of ugly, to be honest. So I kind of like to draw my pi bonds separate to my sigma bonds, but you can do whatever you like. So that would be the bonding in that funky molecule.